Hey, I'm Salwa Mostafa. I'm postdoctoral researcher at University of Olo. We will be giving editorial towards 6G intelligent and secure intent-based networking for autonomous network management. This tutorial is supported by the EU project 6G Intents. The tutorial is divided into two parts. The first part will be talking about the fundamental concepts of intent-based networking. I will be talking in this part, and the second part will talk about the security in network management by one of my colleagues. In the first part, we will discuss what is intent-based networking, what is the difference between IPAN and traditional networks, why we already need IPAN, what are the main enabling technologies and the main high-level architecture of IPAN, and discuss the standardization effort for the network architecture and the proposed architecture by the 6G Intensive project. And then we will talk briefly about the main component of the intent-based network lifecycle and some of the proposed solutions in the 6G Intensive project. So first, let's define what's intent. Intent is defined as a set of operational goals or outcome expected from the network by the network users. Uh, it's uh, it's a declarative way for what they expect as an outcome from the network, but it doesn't specify anything about how to achieve or implement uh, the requirement in the network. We will give a brief examples for what we can consider as intent and what should not be considered as an intent. For example, when we say for a smart city service, ensure traffic signal control traffic uses dedicated and redundant slices that avoid fate sharing. This sentence specifies the desired outcome and set of constraints that should be um, provided for the requested service, but it doesn't specify to the network operator how the service should be implemented down in the network. On the other hand, if we uh, say that configure a given interface with an IP address, this is not considered as an intent, it's a configuration to the network. Another example, when we say maximize network utilization, even if it means trading of service levels like latency or loss, unless service level have deteriorated 20% or more from their historical mean. This also specifies a desired outcome, set of constraints, and some guidance what you can trade and until what percent, but it doesn't specify also how to achieve this outcome. So this is considered as an intent. On the other hand, when we say when interface utilization exceeds a certain threshold, emit an alarm. This considered as a rule and to help support the network operation to take a specific action when some conditions are satisfied, and this is considered a rule, not an intent. So briefly, intent is a set of operational goals or outcome in a declarative way and without specifying how to achieve this service or outcome from the network. So we have intent-based networking where the network has been operated using intent, and the network is able to recognize and ingest the, the intent from different operators or network users, configure and adapt itself according to this intent, and it achieves the outcome without require the operator specifying the details of the technical implementation. In this case, when the network can do this, able to recognize or do these steps, it's called intent-based network. And we have the intent-based system, which is act as the interaction point between the user and the implementation functionality in the network. It's the system that help the user to manage the network and achieve the expected outcome. The advantage of operating with intent is that it provides some kind of data abstractions where the network users do not need to know the low level configuration or operation of the network. It also provides some functional abstractions in terms of management and control, where the users do not need to be concerned with how to achieve the intent in the network. So it gives a high freedom to the network operator to optimize the network to achieve the intended outcome. When we look at why we moved or the network operators are moving toward intent-based networking and then traditional network has been relied on policy-based systems where the policy is considered or defined as a set of rules that users input into the system to manage and control certain events happens in the network, like it's associated with event condition happen. Some events happens, you have some constraints satisfied, then take this action. And these policies has to be defined by the network operator, where they specify under what circumstance what should be happen. Although it have some sort of abstraction because it works in different network domain and devices, and all of these networks or domains have different um, scope. So the heterogeneity of these scopes, we have considered that policy has some sort of abstraction but lower level than intent. When we compare the policy-based systems and the intent-based system, we can compare them from the term of intelligence or AI, as considering the intent-based system as expert systems. They operate on certain knowledge or rules defined for them. And they able to inference and function based on the given rules, but they are not able to learn new rules or adapt to a dynamic environment or conditions changed in the operation until we define some new rules for this new behavior in the network environment. On the other hand, we intent-based systems, we can consider it as a learning system. It's able to learn without depending on some user uh, given rules or script. Users focus more on what they want the network to achieve, not how to accomplish it. And they are able to learn pretty well because automated intent-based network rely heavily on using AI and machine learning in their operation. So now all network service providers are moving toward using intent-based systems than policy-based systems because different users don't have technical details. App developers want to, but do not want to be bothered about what's happening in the network or understand the network to do their jobs, and also the operators want more abstract and robust way when they operate their network. And the complexity of the communication system leads us to move from the traditional manual configuration to simplify the management and configuration in the network in an automated and automatic way where there is less intervention from the human in the network. To achieve this kind of automation in the network operation and management, there are two main enabling technologies that help achieve the intent-based networking. One of them is software-defined network, which consists of which basically decouple the control plane from the data plane, offering the network ability to fastly configure and automatically configure the network. We have it has like the application layer, control layer, and the infrastructure layer, and they communicate. The control layer communicate with the application or the business layer through a northbound interface, and with the infrastructure through northbound interface, with the application with northbound interface. And there is some platforms and hardware that can be used for each of these layers. So the SDN controller usually have an overview about the network topology or resources available from the infrastructure layer, and it also allows for if we look at how the network was managed before pre-SDN and after SDN, we can see that before uh, integrating SDN, we have the control plane with the data plane together, where the control were distributed, and it's hard to reconfigure the whole network. And there are two, it's a vendor specific and low level configuration is required. But now when the control plane is different, separated from the data plane, we have centralized the control that immediately can reconfigure the whole network. The hardware become abstract and vendor agnostic. So this kind of technology help IPAN a lot to automate IPAN to achieve their functions. Then we have the network function virtualization, which decouples the network functions from the dedicated uh, uh, hardware that it runs the service itself. It consists of an application architecture where we have a virtualized network function for different network functions. We have the virtual infrastructure layer, which has a platform that's able to manage uh, the virtual resources and implement it on the hardware, which one of the examples for this management system is Mano system. Before integrating network function virtualization, we have high operating cost because we have hardware per application per site, which was quite high, expensive for network operators. The sustainability, scalability of the architecture, it was complex and um, have a lot of problems with, like, manually we need to manual the network configuration specialized to specific hardware. But after utilizing a network function virtualization, we have low operating cost, and also the network users, they pay as they go based on the services they needed. The scalability of the network become much easier, and the administration and configuration we have, because we all the network function are virtualized uh, in the network. So when we look at these two different technologies, SDN and the network function virtualization, each of them do contribute or complement each other in one way or another to achieve the intended goal for intent-based networking. Like SDN provides separate control and a data plane centralized control, while virtualized network function help it to achieve this separation between the control and data plane. And at the same time, network functions serve the SDN by providing some software to virtualize the control layer, to help in visualizing the control part. So when we look at some examples for how intent-based networking can be enabled using SDN and the network function virtualization, here are very small examples, like when the network users use connect points A to points B through northbound interface. to the controller, they can immediately translate this intent to a set of rules or configuration, or map it to a set one of the policies that can be activated through the northbound interface to the data plane. Similarly, when we use network function and say user wants high security and quality of service when running application A, the network function virtualization orchestrator can translate it to a functionality chain that can be implemented by the controller in specific hardware to achieve the intended intent requested from the network user. Then we move to talk about what is the main high-level architecture of IPAN, or very high description how it should be. It consists of three main layers: business layer, where users express their intent regarding quality of service, service level agreement, some target operational goals, and it's a very high level related to the network and services. And then we have the intent layer, where it executes the sequence of actions required to achieve the submitted intent, and it has to reevaluate and replan at each step when we handle the intent. It has some knowledge about the network and their capabilities and the lower infrastructure, and it has an agent which acts as interface with the through the southbound interface to the physical devices in the network or the different domains in the network. And we have the database that keeps the feedback from the physical layer in the network about the devices and the status from different domains, so that uh, we have a monitoring during the intent life cycle if the intent is able to be achieved or implemented correctly or not. And we have the network layer, which contains the network nodes and the different network domains of RAN, transport, or the core network. And it's also responsible for transferring the network data into a format that can be understand or report back to the network user if there um, it reports back to the intent layer about the status of the network devices. So now we are talking about the effort from the standardization. Now we are talking about the effort from the standardization toward the architecture for intent-based networking. Two of the main standardization organizations toward to that is TM Forum and ETSI. TM Forum has their own proposed architecture for autonomous network as a reference architecture, where we have they divided it to business operation, service operation, and resource operation layers. And they introduced autonomous domain as a set of systems or platforms that are capable of working using closed control loop to achieve certain specific outcome or functionality in the network. And the three operation layers are decoupled from each other, and the intelligence has been decentralized and located within each domain for fast decision making. And it's also introduced zero touch network and service management, which aim to achieve end-to-end service and network management using closed control loops and data-driven decision making by uh, managing different domain using intent. project has proposed their own architecture that relies on introducing distributed intent-driven management and orchestration. It has three main components for management and orchestration: T-Demo, which is responsible for handling vertical services and processing it into the demo. The demo operates on the service level. It receives the intent from the T-Demo or from the vertical tenant directly. We have the network compute fabric, which will work on the resource layer. It acts as an abstract layer on the network resources and technologies. It's quite become demanding in 6G to implement a network compute fabric for resource pooling, for resource pools, and managing distributed resource management. And in each operational domain, we have a separate intent manager that manage independently make decisions, and it has its own intent lifecycle management and closed control loop. And each of the layers in the proposed architecture has a native AI toolkit for fast decision making, and it relies on managing intent that comes in the natural language intent, human language, and it helps to translate it to lower level configuration and management. And it also introduces context aware decisions using reinforcement learning and hierarchical reinforcement learning for resolving conflict and resolution in the intent lifecycle management. And we still in this architecture implement the autonomous domain as in the T-Demo, with local management orchestration at each domain as radio cloud edge. Now we will briefly talk about the main component of intent-based networking. The intent takes place over a complete life cycle, which consists of 5 main steps. First, intent profiling, which receives interact through this step. The network users interact with the network to express their intent, what they expect from the network as an outcome, and it can express their intent in different ways using command line interface, APIs, graphical user interfaces as a drop-down menu to express and it negotiate back with the user to help coming up with a meaningful intent to the network. We have the intent translator, which express the intent in receive the abstracted intent and translate it to lower level network configuration and policies. Then we have intent resolution that solves the conflict between independently submitted intent and intent activation that activates the network function and services. Then we have intent assurance that keep monitoring the intent during its life cycle to ensure the successful deployment of the intent in the network. We will focus on the first two components in the intent life cycle, which is intent profiling and the translation in this tutorial because the time limit. So in these two steps, the main objective is to reduce the gap between every type of user, starting from no technical user to high expert network administrators, and provide an intent language that minimizes the gap between the human and the machine readability, and produce a translation framework that can convert high-level intents into lower-level network configuration and policies. IETF has done some effort for defining intent and providing some classification for intent profiling based on the network type, the intent scope, the network scope, and the intent life cycle. And based on the type of the expressed intent and its scope, different translation methods can be used. So now in the literature, the very common ways to express intents is using template GUI, using natural language processing, using IPAN language, API or command line interface, and different translation mechanisms like templates, mapping, policy, machine learning, all of this. In this tutorial, we will focus on using natural language processing, since the 6G intents focus in managing intents in human language. But I briefly talk about the disadvantage of different methods available so far for intent profiling and translation. The first one is using a graphical user interface, where the users have a drop-down menu to select some options for some criteria defined by the network service providers. And this way is very easy to express the intent and very easy to map it to specific network configuration and services. But the disadvantage is that the user is limited to the predefined scope by the network service provider. They cannot go outside the scope defined for them in the template. Then we have API based, where the users express their intent using command line interfaces JSON files. The advantage of this method is very simplified for the users to express their intent, and it simplifies the intent translation, but it requires some expert knowledge from the users about the network. Then we have IPAN language, with a language specific to communicate with the network, and it's mainly for technical expertise. For example, Nemo language, for example, if we say route else traffic to POP with bandwidth, latency, firewall, so we express different things that can be used from this, and define the intent and its technical language. It's very easy to map it to network policies and service chains, but again, it requires some knowledge from the users. Then we have NLP and machine learning, where the users can express in a human language what they expect as an outcome from the network. It gives high flexibility for the users to express their intent, but the disadvantage is that we have a very diverse range of users, from network operator, application developers, end users, and each of them have their own ways of defining how they expect from the service of the network, which makes the translation process very difficult. So far in the literature, they rely on using machine learning methods like classifying intents based on some abstracted keywords, or and map these keywords to some network policies, and this requires some labeled database, and we have lack of this. And the models needs to be highly trained, which consumes a lot of GPU. And so far it has shown good performance for simple intents, but will struggle when the intent becomes more complex or vague. In 6G intents, we proposed a way for managing the intent in human language, where we use large language models with high capability and reasoning, machine reasoning, and we have domain language and observability to help the translation process. And then we have shown how the intent is passed through the different layers in the architecture, starting from receiving the intent from end users, pass it to in the T demo, translated to a service intent that's passed to the T demo, and in the demo we decompose the intent based on the different requirements using hierarchical reinforcement learning, and produce a resource intent which is mapped later onto the network compute fabric, which translated to decompose it to different actions that needs to be taken by local management and orchestrator at each autonomous domain. One of the work we have introduced for managing the high-level intent received at the T-demo is to utilize RAG, Retrieval Augmented Generation, machine reasoning, and generative AI. And we introduced a framework that utilizes the network database, refine the high-level intent from end users, and convert it to a structured intent. The details of this work and video explanation for it is available because of the time limit. But in summary, we have compared the performance of our proposed intent RAG with vanilla RAG and using large language models directly. We find that large language models tend to hallucinate and add a lot of information outside from the public database, which is not usable for operating the network. So we stick with using the network database through retrieval augmented generation. We also show the performance of our proposed framework from the retrieval part and the generative part, and show how it outperforms the benchmark. And for the generative part, they give close performance because we use the same large language model and the same designed prompt to do the service. Then we have introduced emergent communication protocols where different applications, machine-to-machine communication, where they can, using machine learning, come up with their own language to communicate with the network by using undefined messages and map it to specific network services or that can satisfy the requirement of this application. The details of the work also in the video explanation for it is available, and our aim in this project is to maximize the number of successful associations between the submitted intents and the network slices that support these applications. And we utilize multi-agent reinforcement learning and use MAPPO algorithms for that. The results shows the outperformance of our proposed methods compared to some benchmarks. So this is the summary of this part, and if you have any questions, feel free to ask.